Hi everyone, welcome back to the Microsoft in 29 days self-paced course. In case if you have not registered for this course, so make sure to register for this course. You can find the link of the course in the description of this video. Once you click on the start button after registering for this course, then you can see that you can get access to all the days, like all the 29 days one by one of this series. And if you click on any particular day, so you will get access to two recorded editorials for the problems that I discuss as classwork, and you will get access to the 5 problems for solving them. The 2 problems that we do in classwork, you will get access to submitting them, and you'll also get access to 3 other problems that I give as homework on the same topic. And you can also check your progress amongst your peers in the leaderboard. So make sure to enroll for this course, make sure to register for it. It is completely free of cost. You can find the link in the description. Let us discuss this problem, which is binary number a multiple of 3? So the problem says that you will be given a binary number and you have to find if the given binary number is a multiple of 3 or not. Okay, so the number can be large. It is recommended to finish the task using one traversal of the input string. So the problem says that they will give you a binary number. Okay, in this problem they will give you the binary number. They will give you the decimal representation of it. Okay, they will give you the decimal representation of it. But suppose that if I give you any number, right, if I give you any binary number, let's say I give you any normal number, so I give you n is equal to, let's say, 6, so you will say that this is divisible by 3, right? If I give you n is equal to, let's say, 9, so you will say that 9 is also divisible by 3. If I give you n is equal to 11, so you will say that okay, this is not divisible by 3. If I give you n is equal to, let's say, 15, so you will say okay, this is divisible. But how do you check? So you will tell me that okay, what we could have done is, if we have been given this number, then we could directly do the modulo with 3. If the answer is 0, then if the remainder is 0, then we can say that okay, it is divisible, otherwise it is not. But when you are in an interview, let's say of company, like this question has been asked, by the way, in Amazon, Microsoft and other companies. So when you are in an interview, so the interviewer will not expect you this, okay, because this can be told by anyone. So what they will expect is, like, if you have to think optimally, because they are saying that if the number is large, like suppose they give you this number s, so you will, like, suppose they give you s is equal to 0, 1, 1. So this is nothing but the decimal representation, and 0, 1, 1 is nothing but 3 itself, right? 0, 1, 1 represents, in terms of binary, it represents nothing but 3. So you will not tell the interviewer that you will first of all make the decimal number from it and then divide it, like modulo it by 2. If it gives modulo it by 3, and if it gives the remainder as 0, then you will do it. No, you will not say this. What you can observe is, there's one observation, like you will always have to think, like whenever you are asked to optimize, so if you don't want to deal with the number itself, so you can observe that we can deal with the bits, right? We can deal with the bits, and in this problem actually you have been given the bit representation. But suppose if instead of the string you were just given the number itself, then also you can deal with the bits. You can do something with the binary representation of the number, and you could have got to a conclusion that whether it is divisible by 3 or not. How? So let us say that if we have a number, right? Suppose that we have a number n is equal to 7 or something, right? Suppose we have any number, and suppose that number is represented like in its binary representation is ABCD, where ABCD, all these values will be nothing but 0 or 1. Okay, so let's say I write it as, let's say there is a number and it has 7 different bits or something like this. So let's say this is the number that I have developed. Okay, suppose this is the binary representation of a particular number. Okay, this is nothing but the binary representation. Okay, so what you can do is, you can observe some of the things in this part. Okay, so let's say you try and make the number, right? So if I tell you that okay, you have to make the number, so if I give you, let's say, 0, 1, 1, something like this, so you'll say that this number's contribution is 2 to the power 0, this number's contribution is 2 to the power 1, this bit's contribution is 2 to the power 2, right? So you say that 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 1 into 2 to the power 0, right? This is what you try to do usually. So what you can observe in this part is, you can observe one thing here as well, that what I can do is, I can say that this will contribute 2 to the power 0, that is nothing but g itself. This number will contribute, this bit will contribute how much? F into 2 to the power 1, so that is nothing but 2f. This number will contribute how much? E into 2 to the power 2, that is nothing but 4e basically. So this is how we can write it. So let us quickly write this so that we can generate the number n. Suppose we try to generate the number n. So that will be nothing but g plus 2f plus 4e, okay, plus 8d plus 16c plus 32b, okay, plus 64a. Okay, suppose this is the number that I have. Now what I can do is, if I try to rearrange this, right, so I will try to make most of the numbers divisible by 3. So if this is 2f, so I can add 1f to it, and I can, like, to this expression, if I add 1f and if I subtract 1f, then I can get it. So what I'm saying is, suppose I write it like this, okay, if we observe this particular number, so what we can do here is, suppose if this number has been given to us, so I can add 1f and I can subtract 1f as well. So let's say if I add 1f, so g, if I add 1f to it, so this will become what? This will become nothing but 3f plus this e is extra, right? So one of the minus f is there, right? So one of the minus f is there because I have subtracted. Then if I see e, so I can write it as 3e, and I can have 1e extra here plus c, right? That is extra. Then I can to this 8d I can add plus 1d, and I can subtract 1d as well from this expression, correct? Minus d also I can do. Then if I have like 16c, so in terms of 16c we can write it as 15c, and I can add 1c extra, that is here, right? Then what I can do is, if I have 32b, so I can write it as 33b, and I can subtract 1b from it, right? Then if I have 64a, so I can write it as 63a, that's divisible by 3 actually, and I can write it as plus a. Okay, now what I can do is, like, once I get this particular expression, right, one by one, so what I can do is I can club them together. So let's say if I club, right, so if I club them together, so I'll get what? G plus, like, you see, this is a positive expression, this is a positive expression, g plus e, okay, plus c, okay, g plus e plus c, and plus a as well, okay, plus a. So these are the expressions that I'm going to add, and which expression I'm going to subtract? Minus f, minus b. So these are the expressions that you can see. So minus f, minus b, and minus d as well. So I'll write them in plus format. Like, if I'll open the bracket, if I'll open this, so they will all become negative, right? So I've added them together, right? So this much part I have to add, this much subtract. So this will be the part, okay? Plus what? Plus this part, plus this whole part, that is this part. That, you understand this? Like this part, 3f, 3e, 9d, 15c, 33b, and 63a. Can I say that there is one thing in common for all of them? The one thing that's common in all of them is that all of them are divisible by 3. So I can say that what I can do is, I can take 3 as common. When I take 3 as common, so what will happen? If I, in this expression, in this particular given expression, if I take 3 as common, so it will become nothing but, what? It will become something like f plus e plus 3d plus 5c plus 11b plus 21a. Okay, now you have to notice this part, that if I talk about this particular segment of the expression, so this expression is already divisible by 3, okay, because it has a factor 3 to it. Like every number here, you can see, is divisible by 3. So if I have clubbed them together, so this complete expression is divisible by 3. So what will decide whether this complete expression, right, this segment is completely divisible by 3? So if I want to check that overall this expression is divisible by 3 or not, which is nothing but the numbers representation itself, which is nothing but the complete number, okay, in terms of decimal. So I can say that what I need to do, I need to check whether this part is divisible by this part, that is g plus e plus c plus a minus, okay, f plus d plus b, whether this expression is divisible or not. Okay, now if this expression is divisible by 3, then the number will be divisible by 3. Okay, so what is this expression signifying? So if I'll observe, right, so what number did I write? I wrote the number as a, b, c, d, e, f, g, h. Okay, suppose I wrote it till g. Okay, so you can observe that a, like this, there is a a here, okay, then c is here, e is here, g is here, right? You can observe this part. A is here, b is here, like a, then c, a is getting added with c and with e and then with g, right? This is the addition part that I'm doing, this part. Okay, similarly you can observe what is the subtraction part, this b, this d, and this f. So I can say what? I can say that this is nothing but set bits, right? When will these numbers contribute? Actually, these numbers will be contributing if they are 0, right? So they will not contribute actually, right? You can observe if b is 0, So it will not actually be contributing. So these numbers will be contributing actually when they are 0, so they will have no significance. But when they are 1, right, then they will be contributing. And what do I say 1? When I say 1, it means set bits, right? So I can say this is what, if I try to do the naming part here, like 0 1, indexing part 0 1 2 3 4 5 6. So you can observe one more thing here, that there are some bits present at the even position and some bits present at the odd position. So I can say that if the count of the, right, if the count of the set bits, right, if the count of the set bits at the even position minus the count of the set bits, okay, at the odd position in the given number, in the binary representation of the given number, okay, if it is divisible by, if this expression, right, if this particular thing, if this value, if it is divisible by 3, then the whole number actually is divisible by 3, correct? If this expression, which signifies nothing but the count of set bits in at even position and the count of set bits at odd position subtracting, so this expression, if this expression is divisible, then this, if the count of set bits minus set bits at the even position, okay, minus the count of set bits in the binary representation of this number at the odd position, if this difference is divisible by 3, then this means that this whole expression is divisible by 3, and which in turns means that overall this number is divisible by 3, because this expression was already divisible by 3. Now this will also become divisible by 3. So you can observe this part very, very clearly. So that is what we have to do in this particular question. So I think that this much is sufficient. You can understand. So suppose you were given the number n itself, okay. So if someone has given you the number n itself, so you will say that in logarithmic of n, in log of n, because you will deal with the bits of the number. If you are just given the number, decimal number, so you will just deal with the number, right? Deal with the bits of the number, and you can get a log n, right? You can get in logarithmic of time, log n time, because you will be just dealing with the bits of the number. So either it will be maximum 32 or 64 depending on integer or long. So that much is the time that you will take. Basically, that's log n, okay. Or you can say that if you are given the string which represents the binary representation, right, of the number, so in that case you will take that, say that you will take the iteration through the string. So that is nothing but the length, that is nothing but the size of the string. That much iteration you will take in this case. So let us quickly try and code this problem out. What I would be doing here is I'll be having the int the count of odd set bits, right? So I'll write C odd, that is the count of the odd set bits, and I'll have C even as well, that is the count of even set bits at the even position. I will iterate through the string. So int I starts from 0, I is lesser than the s dot size, you can say, right? And then I'll do an I plus plus 1 by 1, and I'll check that if the ith bit is set, okay, if the s of I is equal to 1, here this is a string, so I have to check s of I is equal to character 1 or not. If it is 1, then I will check that if s of I mod 2 is equal to 0. So if this bit is set and it is an even position, then I'll say that, okay, the number of set bits at the even position I'll add, okay. Otherwise, what I will say is, otherwise we can say that I will add what? I will add the number of odd, like I will increase the number of odd set bits, right? Set bits, I will increase the number of set bits at the odd position. Otherwise, if this bit is set, so if the position is even, then I increase the number of even set bits. Otherwise, if this bit is odd, so that means that number of bits that are set at the odd position, that will be updated. So I'll say that count of odd plus plus, okay. Then what I can say is, if in the end, if I check, so if the count of like the even set bits, if the count of the set bits at the even position minus the count of set bits at the odd position, modulo 3, if it's equal to 0, if this expression is divisible by 3, then that means the whole expression would be divisible by 3, okay. In that case, as I mentioned, I'll return a 1 in this case, indicating that the number is actually divisible. Otherwise, I would return a 0 indicating that, okay, the number is not divisible by 3. Let us try and quickly compile this code to see if there is any error. Okay, so it seems to work on the samples. Let us try and submit this code as well. So you can see that our solution was able to pass all the test cases. In case if you understood the explanation for this problem, which is very unique, so make sure to hit the like button and comment down understood as well. Thank you. In this video, we will discuss the problem maximum and value. The problem says that we have been given an integer array which has n positive elements, right? So an integer array is given to us which has n positive elements inside it. So there are n elements, n integers, and the task is to find the maximum AND value. So what do we mean by AND value? So basically AND is nothing but AND here means the bitwise AND. So I need to choose two different indexes of this array, and I need to take the AND of the elements present at those two different indexes of the array, and then what we need to do is we need to return the maximum AND value between any two elements in this array, right, which are at different indexes. So let's suppose that if I had an array, okay, suppose that if I had an array like this. So what we want is, we basically want to choose one index, let's say I, okay, we want to choose one index I, we want to choose another index j which can lie inside the array, and we want to choose these indexes such that I is not equal to j. So I and j should not be pointing to the same element, right? They should not be at the same index. I and j should not be at the same index. And what we want is, we want a pair such that the element present at the ith index and the element present at the jth index, when I do a bitwise AND of those two elements, right, when I do the bitwise AND for these elements, okay, so then the bitwise AND should be maximum possible, right? It should be maximum possible. It should be as maximum as it can be, right? It should be the maximum. So I want the bitwise AND between any two elements of the array which are at different indexes to be maximum. So one of the ways that I can think of is, like, if I have been given an array, suppose I was given any array. So one of the very brute force approach that we can think of is, let's say we start our index I from here, right? Then what we can do is, we can check this ith element with this element, right, one time. Then I can check this element with this element, okay. Then I can take the AND value and I can check what is like whether that AND value is maximum or not. Then I can check this with this element with this element. Then I can check this element with this element. Then I can check this element with this element, okay. And then one by one I can keep on taking out the AND, and I can keep a track of the maximum, right? After that, again I can do what, I can move my I here, and then I can check this element with this element, the AND with this element, the element of the AND of this I with this element, okay. Then the AND of this I with this element, and I can check the AND of this I with this element. So basically what I'm trying to do is, I'll try to check the AND value, right? I'll try to check AND value, okay, AND value of the pair for all possible pairs of the array. So how can we do that? So basically, as you can see, my I will be constant, like at one point of time I will be there. Then I'll move my j here. So this I and this j I'll check. Then I'll check this I and this j. So j will move here. Then j will move here because I want to check this I and this j. Similarly, j will move here because I would like to check this I, this element array of I and this element array of j, right? Then I will like to check this element array of I and array of j, correct? One by one I will like to keep to check. So what we can do here is, if we want to do it like that, so basically that's very brute force approach. What we could have done is, we can do what, we can say that, okay, I starts from 0, I is going to be lesser than n, then we can do an I plus plus, okay. Then what we can do here is, we can say that, okay, j starts from 0, then j is lesser than n, j plus plus, no, j starts from I plus 1, because you will be starting from 1 ahead, right? So j starts from I plus 1, j is lesser than n, then we can do a j plus plus, and we can keep a track of maximum. So initially we can mark the maximum as 0, maximum AND value. Then what we can do is, we can say that mx is equal to nothing but maximum of mx comma array of I and array of j, right? So we can simply take the AND value of both, and we can check, right? We can check that if it up, like we can simply say that we'll keep on updating our maximum mx, and in the end the mx will be returning what? We can simply return the mx, and mx will store the maximum AND value between any two pairs, because I am checking what, array of I and array of j, right? Now let's quickly talk about the properties of AND, bitwise AND as well, before we move forward. So the property of bitwise AND is that if I do 0 and 1, like suppose I do 0 and 1, so it will be 0, okay. If I do 1 and 0, again I'll get 0 as the answer, right? If there's a bit, let's say 0, and I do AND with another bit 0, I'll get a 0 again. If there's a bit 1 and I do an AND with 1, so I get a 1. So basically the observation is that for doing the AND, for getting 1, the both the bits should be 1, right? If both the bits are 1 for a particular position, then I can say that, okay, at that particular position also the AND value will be 1. And since I want to maximize the answer, right? So as you know that how is a number built, right? Let's suppose that first number is built using some let's say first number is like this, 1 0 0, then 1 1, okay. Let's suppose that the second number is something like 1 1 1 1 1, all the ones are there, right? If I do an AND operation here, right, if I do the AND operation between the two numbers, I'll get a 1 here, I'll get a 0 here, I'll get a 0 here, I'll get a 1 here, I'll get a 1 here. So basically I'll try to do what, I'll try to have as many ones as I can, okay, according to the positions. And for doing this, I can say that I will want what, I wanted a 1 here as well, I wanted a 1 here as well. So I'll try to get, for every position I'll try to see that I can get as many ones as possible for me, right? This is one thing. Now how can we do this particular problem? So what we can say here is, if we have been given any number, So suppose if we have been given any number, like suppose we suppose we have to build the number. So if I can say that, suppose these are the bits, like actually if the number suppose can go till 10 to the power 9, so there will be 32 positions, 32 different positions. If the number is 10 to the power 5, then they can be let's say 16 positions, like this. So suppose there are several positions, right? So if I want at every position I want a 1. So basically what I can say, if I want a 1 at every position, so one thing that I can think of is, like one thing that I can easily think of is that at every position I want a, like at every position mostly I will want a 1. So you will think that okay, at least two numbers should be having the bit 1 at that particular position. This could be one thing. Okay, this could be one thing. But I will also tell you one thing. Suppose after doing AND you get one of the answers, like suppose one of the answers you get as 1000. Okay, suppose you get this as answer, right? Or suppose that you get 100 as the answer, right? Suppose after doing some AND operation you get the answer as this, and suppose the second answer that you get is something like 1 1 and 0. So you will think that okay, this number is having more set bits, so it will have the maximum answer. No, because if you will see, this number is what, in terms of binary representation, it is nothing but 3, whereas this number is nothing but 4. So actually it does not depend on the number of bits, it depends on this value, right? On the maximum most significant bit, MSB. If the most significant bits are there, then they will contribute more, because this bit contributes 2 to the power 0, this will contribute 2 to the power 1, this will contribute 2 to the power 2. I will want as many maximum bits set at this particular position as possible, right? So I'll try to see it like this. And when you try to see it, so this is the position 0 1 2 3, right? So basically I will try to see it from the back side, like I'll try to have the like bits which are contributing more to my number. I'll try to set them up first of all, right? I'll not care about the smaller bit. This is one thing. So I will iterate from the back. Now if you think, so if we could do a brute force obviously, but order of n square time is taken. So if we want to minimize this, so whenever you are given bit problems and whenever you are getting brute force as very long time complexity, so what you can think of is, you can think of dealing with the bits itself. If you deal with the bits itself, then the answer becomes possible, right? Then the time limit is like, then the what happens, then the time taken by the program or the algorithm is lesser, because you are dealing with the bits. They can be maximum 32 or 64 bits, right, in terms of integers or long. So what you can do here is, we can easily see this part, that suppose if I had, like if I wanted to, let's say if we talk about certain positions, right? Suppose all the rest of the positions here are 000, that we like, this is the case. Okay, suppose we want to have these positions. Okay, suppose we have these positions and we want some person, like let me use single this thing. Okay, suppose I want here a 1. Okay, suppose I want at this particular position I want a 1. So if I want a 1 at this particular position, right, because I will be doing what, I'll be first of all be focused, as I said, if there's a 1000, okay, so it is always going to be greater than 1001 representation. 00 4 times 1 position. Why? Because it always depends on the maximum set bit position. If a bit is set here, so it will contribute so much that others bit contribution would be exceeded, right? So that's why I will try to do this. I will try to see it from the back, right? From the highest, most set bits, most significant bits, I'll try to set them first of all. Okay, so if I want to set a bit 1 as here, so can I say that I want two numbers? I can say that I want two numbers which have a bit set at this particular position. Okay, then what I will want is, I will want that, okay, let's say I get this bit as 1 in both the numbers, right? And I set this as 1. Okay, so this will be the result, suppose. So I say that, okay, this particular bit, at least this particular bit is set. So once I set this particular bit, okay, once I set this particular bit, so what do I want? I want this bit to be set as well. Okay, I want this bit to be set as well. So suppose I get two numbers. Suppose I get number like 0 1 something 0 1 1, and suppose I get 0 1 1 1 1. Okay, so you will say that let's take this number, because what will happen in that case, we'll be able to set this particular bit. Okay, you will say that, okay, we can set this particular bit as well. No, you cannot do that. There's a pattern that you have to observe, right? You have fixed this, right? You are wanting that suppose you get two numbers such that this particular bit was set in those numbers, right? So you want the numbers now to be such that they should have these bits as set, right? At least this much should be the answer, right? At least they should be this much, right? They should be having a bit set at this particular position at least. Then I don't care about the rest of the part, but like we can think about it, but we want this bit to be set at least, right? We want this bit to be set at least. So this is one thing. We want to follow this pattern, right? We want this particular bit to be set as well, right? This is the pattern, right? We want at least this much is what we expect, right? Other than this, if we can set this particular bit, then it is fine. That will help us to maximize the answer. Like, so we will find the numbers in such a way that at least this this much part is set in that particular number, okay, and then I will try to set this particular bit. If I can find two other numbers which have this, which can help me to set this particular bit, okay, and help me to set this particular bit, then it's fine. If I don't find, then I'll put a 0 at this position. Suppose I put a 0 at this position, okay, then what will happen? You can see that the number is 1 0, okay. So if I get this, so I'll try to find two numbers, right? I'll try to find, like, will I, like, if this is the position, so will I have this thing? Suppose these are the numbers. So if I take the AND of this, so you'll say that, okay, we can have a 1 here. No, you need to find two numbers such that this configuration is also followed by them, okay, at least this configuration, right, at least this pattern is followed by them. So for that, what you can do is, you will want numbers like 1 0, let's say 1 1 1 is there, or something, 1 0, and 0 0 0 something is there, okay. If I do the AND, so this will give me 0 0 0 0 0, okay. But suppose I get some number, I get a particular number in which, suppose that this particular bit is also set, right, at this position, it is set, okay. So if it is at least following this much, right, at least this much should be there. If I get zeros here, I do not worry, but at least these bits should be set, right? The larger bits should be set, because they will give me the maximum number. As I mentioned, 100 does not, like, it will give me the maximum number compared to 011, okay. So I am not concerned about setting more bits, I'm concerned about setting the larger bits first of all, okay. And I need to follow this pattern, right? At least those bits should be set, and if I can set the lower bits as well, so that will be an added advantage for me, okay. So I need to follow this pattern. I need bits which follow this pattern. So I can say that, what I can say that for the rest of the part, I want to set this particular bit, okay. So suppose I want to set this particular bit, so I will want a number. Suppose I want this bit to be set, okay. If I want this, so what I will do is, if what is the position, I know this position, correct. So if I want a bit to be set 1 here, so I can say that, suppose there's a bit 0. If I do left shift with 2, so this is the position actually 2, right. So if I do left shift 2, so this will become 1 0 0, correct. So I'll have 1 0 0 here. So if I do the AND of the result with this particular bit, so actually what configuration I'm currently wanting? I'm currently wanting at least this particular configuration, right? At least this particular combination. So if I get, right, suppose if I get any particular two numbers such that at least they are giving me this much, right? At least they are equal to this, like, suppose this is the result, right? At least this part. Suppose this is the pattern, right? Correct. So if I get two numbers such that I can at least get this much part, if I get at least the count as 2, then I will say that, okay, we can update our result to this part, and we can, in the result, we can add this particular bit as well. Otherwise we'll not add it, and similarly we'll follow the same condition for the other positions as well. For the other position, we'll look that, okay, this much pattern is followed or not. At least they should have this much bits as set, and if there are two numbers such that at least this much bits are like this, 101, okay, and then 10100, and then if I can set this particular bit as well, like if I can mark it as 1, then I will mark it. Otherwise, if I cannot, then I will mark it as 0. If I can mark this bit as 1 in two numbers such that they follow this particular pattern, at least that 1010, at least this much is what I'm getting for these positions, and then for this position, if I get a 1 here set, then I will be fine, and I'll add it to my answer, okay. So that is what we will try to do. We'll try to see that if this pattern keeps on following, right, because I want to set the larger bits, I want to keep the larger bits set as much as possible, right. So this will be the approach. Let us quickly try and write the code. Now if you will observe in this part, if you will follow the constraint, so constraint is that n is 10 to the power 5, okay. So if suppose n was given as 10 to the power 9, if n is 10 to the power 9, so the bits can be from 0 to 32, right. So that's nothing but 0 to 31, that is 32 bits. If suppose n is equal to 10 to the power 18, so that's nothing but from 0 till 64 bit, like 64, right. So 0 till 63, that is nothing but 64 bits, okay. If n is equal to 10 to the power 5, so that's nothing but just 16 bits, right. I want just 16 bits. That's nothing but from like 17 bits, you can say actually. So that will be nothing but from 0 till 16, okay. So you can run the loop for 0 till 16 bits only, right. So let us quickly try and write the code for this particular approach. Well, first of all, get this function, okay. I'll initially mark the result here as 0, okay. Then what we will do is we'll iterate from the back of the bits, right. We'll try to set the larger bits first of all. So let's say I run a loop using bits. You can also use I in place of bit. So I'll say that I'll run until the bit is greater or equal to 0, and I'll simply do a bit minus as well, okay. Once I do that, so what we will check is we'll check the count, okay. We'll write a function which will give us the count. So we will do what? We'll pass the check function here, okay. We'll pass the check function, and we want what? We want the current result, whatever we had. Now we want to set what? We want to set the current bit, right, current bit. So if I want to do that, so I'll do one left shift bit, and I'll see that, I will try to see that whether I can set it or not. If I get a configuration, if I get two numbers such that this much answer has been made, right, this much expected answer has been made, then if the count is greater or equal to 2, so that means if I get at least two numbers which have this particular configuration, that is result or one left shift b bit, okay, if this is set, Okay, so in that case I'll update my answer, otherwise I'll not update my answer for this particular bit. Otherwise I'll keep the bit at 0 for that particular position, otherwise I'll update the answer. Okay, so I'll pass the array here, I'll pass n here as well. Okay, now if the count that I have, if it is greater or equal to 2 for this particular position, in that case what we'll do is we'll do result or is equal to, we'll do result or is equal to 1 left shift the bit. So we'll set this particular bit. If there are at least two numbers in the array that are helping me to keep the previous pattern same, and as well as set this particular bit at the current position, in that case I'll update the answer. Okay, and once I have updated the answer every time after for every position, I'll say simply in the end I'll want to return the answer. But before that I also want to write the check function here. Okay, so let's write the check function in check, which will be returning me the count. So first of all I'll pass, let's say, the pattern that I want to follow. Okay, then I will pass the array as well. Okay, and we'll pass the integer n, right, that is the size of the array. So we will do what, we will initially mark the count here as 0, right, that is initially no two numbers will be following the pattern. So what we will do is we will try to see that if we'll try to search from I starts from 0, I is less than n, and I plus plus. Okay, and if there is a number, right, if there is a number, let's say the current number is rfi, so if rfi, okay, and the pattern, right, doing an and with the current pattern, if it gives the pattern as the answer, right, if it is equal to the pattern only, if it is equal to the pattern itself, right, so in that case we can say that okay, it is following the pattern, so at least one number is following, so you can implement the count plus plus. Similarly we can do it for every number. Okay, in the end we'll return the count, and if the number of numbers, if the count of the numbers that follow this particular pattern, if it is greater or equal to 2, in that case we can say that okay, we can set this particular bit as well, and we'll set it in the final answer as well, right? So every time we'll return the answer. So let's try and compile this to see what happens. Okay, so we are getting a compilation error, n was not clear, so we can mark it as small n. Now let us compile it. So it works on the samples. Let us try and submit this. So you can see that our solution was able to pass all the test cases in the very first go. Now talking about the time complexity and the space complexity of this approach. So since we are not using any extra space, so the space complexity will be nothing but order of 1. And talking about the time complexity of this approach, so in this case, when the n value is given as 10 to the power 5, so it will be nothing but I'm checking for 16 different positions, 16 different bit positions, right? Or you can say 17 different positions, right? And the every time I'm iterating through the array, so n into 17 will be the time taken for this particular approach for when n is given as 10 to the power 5. Okay, in case if you understood this explanation, so make sure to hit the like button and comment down understood as well. Thank you.